All right. So far, we've seen that weak nucleophiles like water, alcohols, and amines react readily with acid halides, acid anhydrides, thionyl chloride, and sulfonyl chlorides. Even though these nucleophiles are weak, the polar pi bonds, specifically that carbonyl and sulfonyl, right, the C double bond O and the S double bond O, that's a sulfonyl, are reactive enough that they compensate for those weak nucleophiles. Now, by contrast, we also saw that esters are a lot less reactive than at the carbonyl carbon because of the resonance involved in leaving group, right? And so, because we've got that resonance stabilization, esters do not undergo nucleophilic addition elimination reactions under normal conditions with weak nucleophiles. So we learned that was a no-go. All right. However, transesterification will take place with a small amount of a base, and so that's considered to be a catalytic amount. Moreover, right, the base isn't consumed in this reaction, so it's definitely a catalyst. Okay. Now, let's look at the mechanism for this transesterification. When we start off, we're going to draw our reactants. All right, so there's our reactant, and then we have this base. And as we know, the sodium is a spectator ion, so it leaves, and we're left with a negative charge. Now, this is going to go through nucleophilic addition. And when this goes through nucleophilic addition, these electrons come here and attack there, and those electrons go back up on that oxygen. Now I'm just looking back and forth and making sure I'm drawing all my carbons, right? And all right, so now I'm here. We've got the oxygen with its negative charge there. I'm going to pull that O down. All right, and now we have the new OCH3 group attached right there, okay? So this is going to go through a nucleophilic elimination. And a tetrahedral collapse. So what happens, right, are these electrons go down and those electrons go on that oxygen. And so right, and now we have our new ester here, okay? Then how the catalyst is regenerated is we have this guy here and that protonated OCH3 here. It will come out and it will grab that proton and those electrons will go there. And then that catalyst is regenerated. So we regenerate the catalyst in a proton transfer step. Now, because water and alcohol behave similarly, it might seem that a base could be used to catalyze the conversion from an ester to a carboxylic acid. And so let's look at that for a hot minute. So here's our ester and our carboxylic acid, right? And what we see here is that hydrolysis does take place to produce, at least with the ester, the carboxylic acid initially here, right? But that carboxylic acid is then rapidly deprotonated into a base, okay? So because of this, the base is consumed in the reaction. So it makes it So we call this a base promoted reaction instead of a base catalyzed, because we don't regenerate that same base that we started with or the same catalyst. And so specifically, this is again an example of a saponification reaction as well. Now, if we look at the carboxylic acid, a similar proton transfer takes place when it's treated with an alkoxide anion, and that makes it unfeasible to convert that carboxylic acid into an ester under basic conditions. So there's just no further reaction. Now, transesterification can also be acid catalyzed. So when we look at this reaction, this is an acid catalyzed reaction. We've got a catalytic amount of a strong acid like sulfuric acid, and that is going to facilitate the production, in this case, of hexyl acetate. Fun fact, this hexyl acetate is found in gummy candies. So it's synthesized a lot in the food industry. It has a bittersweet, fruity taste, and so it's a flavoring agent. So that's one of the things, it's a flavoring agent. So we use a catalytic amount of a strong acid. So let's look at the mechanism for this, okay? When we start and we look at this mechanism, we undergo a proton transfer where we started with that alcohol, and that's protonated because of the sulfur there. Now I'm just going to do parentheses in 5. Okay. All right. So proton transfer is the first step. These are coming. Those electrons are going to come out, and they're going to grab that proton, and those electrons go on the oxygen. Now, when that happens, here we are. And what we see happening here is that these electrons go there, right? And those electrons go up on the oxygen. And when that happens, that's a nucleophilic addition reaction. Okay. And so when we look at that, let's draw our products. I'm going to draw my alcohol here. I'm going to move that OCH3 down here. Okay. And then I'm going to look at the oxygens attached that formed a new oxygen bond. Let's move hydrogen here. Put the electrons there. We'll put a positive charge there. All right. Now, what happens at this stage is a proton transfer. So that same kind of alcohol with the 5 carbons, 6 carbons comes back in, right? And what we're going to see is that these electrons here are going to come down, and they're going to grab that proton. And those electrons are going to go back on the oxygen. So when they do that, right? We have that. Okay. And so what happens is deprotonation stabilizes the nucleophile. So this is pretty stable. And then the leaving group's ability, so this is the leaving group here, that leaving group's ability increases on protonation. So it is now, so we're going to go through a second proton transfer. right? Where what happens here is that these electrons come out and they grab a proton here. And then those electrons go back on the oxygen. Now, when that happens, we have this molecule here. And these electrons are going to go down. We're going to see a nucleophile elimination. So they come down here. Sorry, I switched colors on you. And then these, that's our leaving group. Okay, so protonation makes that a really good leaving group. So now we have a nucleophile elimination. Okay. And then in this next step, we're going to get a proton transfer. Right? Where these electrons are going to go here, right? And those electrons are going to go on the oxygen. Okay, and so now we have our product, right? And then the acid catalyst is regenerated through that proton transfer. Right like that. So again, catalyzed, we are going to regenerate our equation. Regenerate our catalyst. So if it's catalyzed, we regenerate it. If it's promoted, then it's something that speeds up the reaction and increases the rate. But what we see is it's not generally regenerated. Okay. Now, unlike what we saw previously under basic conditions, the conversion of an ester to a carboxylic acid can also be acid catalyzed. And so this is an example of something called an ester hydrolysis. Now, this reaction, like an acid catalyst transesterification, is reversible. So achieving a high yield of the product often requires using Le Chatelier's principle. So to avoid a lot of complications, instead of doing that, chemists generally prefer to carry out the hydrolysis of an ester irreversibly under basic conditions, which we saw like kind of back a few slides, equation 23-26. Unless the basic conditions lead to an undesirable side reaction. Now, the esterification of a carboxylic acid can be acid catalyzed too in what's called the Fischer esterification reaction, which is shown here. Emil Fischer was a German chemist and Nobel laureate, and he was really the first report these kinds of reactions, and so they are named for him. Now, acyl substitutions under acidic conditions are not limited to esters and carboxylic acids. Amides, which are even less reactive than esters or carboxylic acids, do not react with weak nucleophiles under normal conditions either. So, under acidic conditions, the amides can undergo hydrolysis to produce a carboxylic acid. And that's what we're seeing here. So the acidic conditions here are super important. So let's look at that mechanism. All right, so let's start by drawing our reactants. Okay, and it's first going to go through a proton transfer. Where these electrons are going to come out and they're going to grab that proton, and those electrons go back on that oxygen. Okay, now we a lot of times refer to this as that CO, or that carbonyl group, being activated. Okay, and so that makes the carbon of the carbonyl super partially positive. Okay, and so what's going to happen here is that we're going to go through a nucleophilic addition where these electrons are going to come in, they're going to attack that carbonyl carbon, and those electrons go up on the oxygen. So nucleophilic addition. Okay, now when that happens, what we're going to see here is there's a single bond here to the carbon, to the hydrogen, nothing's changed there, right? Okay. Then there's an oxygen, the hydrogen, and a positive charge here. And then up here, there's an oxygen, an alcohol group. All right, so we've redrawn that with our new bond. Now, what happens here is a proton transfer, where water comes in and it steals that proton, and those electrons go on that oxygen. Right? And so what happens is this leaving group, just like we saw before, its ability to leave increases on protonation. So the next step here is going to be another proton transfer. Right? Where these electrons come out, they grab that proton, those electrons go back on the oxygen. So, redrawing this, right? We have a carbon here, it's bonded to a hydrogen. There's an alcohol here, and there's an OH here. Okay, and then we've got a positive charge. Sorry, I was just checking all my charges. We have a positive charge there. Now this is where we get the nucleophile elimination. Where these electrons come down here, okay? And then those electrons go on the nitrogen. Now, when that happens, we have this molecule here, right? And this molecule here, and it will undergo another proton transfer where we're going to come and grab that, and those electrons go back there. All right. And so that is how an amide undergoes hydrolysis. You'll see we end up with a carboxylic acid functional group and an amine. Now, this is acid protonated rather than acid catalyzed, because you'll notice the catalyst isn't regenerated. The next set of reactions that we learn in this chapter are the Baeyer-Villiger, right, or sometimes Williger, depending on how you want to pronounce it, oxidations. So when we look at this particular reaction, when diphenylmethanone, which is also called benzophenone here, is treated with a peroxy acid, and this particular peroxy acid is called M-chloro-per-benzoic acid, right, which is abbreviated as MCPBA. Now, you need to know that abbreviation because these reactions will either show you this molecule or give you that name. So you need to know that those are interchangeable. A phenyl benzoate is produced, okay? This was named after Bayer, who was a German chemist. You can see his picture there. And then Victor Villiger, which was a Swiss chemist. And you can see his picture there. Now, the mechanism for how this occurs, where we're going from a ketone to an ester group, right? So that's what we're seeing. We're seeing a functional group transition here. Is very similar for the mechanism for acid catalyzed transesterification. So because it's so similar, I'm just showing it to you here, but I do want us to walk through it. So when we walk through this reaction, what we see are that these electrons come out and grab this proton as part of a proton transfer. And then these electrons go back on this oxygen. The next step is a nucleophilic addition. So this is where the MCPBA comes in, and we're going to see a nucleophilic addition here, and that's a leaving group, right? No, sorry, not a leaving group. That's where those electrons go up there. It doesn't leave. But one of the things we'll notice is we talked about this carbonyl group being activated, and so you can see that being there. The next step is a proton transfer, where these electrons come out and they grab that proton. Those electrons go back on the oxygen, and so now that's neutral. Then this is where we have a leaving group. We have the nucleophile elimination, where these electrons come back and they form a double bond there. And then here's a wickety wild thing that happens. So these electrons then come over here and form a bond with that oxygen, and then these electrons leave, and you have an oxygen-oxygen bond that's broken. So this is your leaving group, okay? But now what we've established is a new carbon-oxygen bond and a carbon bond here, right? Now we end up with a proton transfer, and we now have our ester. So we go from a ketone to an ester. And this is kind of that new wickety wild thing that we get to learn here, which is super fun. So this fourth step, because this is new, I want us to focus on this for just a second. The bond to this carbonyl carbon that breaks depends on what we call the migratory aptitudes of the groups attached. So when we talk about migratory aptitude, we're talking about what's the aptitude of this guy moving and making a bond here. Okay. So when we think about that, right, what we find, okay, is that the methyl group is here. Okay. Then we have the primary, the secondary, the aryl, the alkyl, right? And then the hydrogen here, where this kind of is the best and that's the worst. Now, these aptitudes roughly follow the order of cation stability, right? Right? And so some studies have shown that the migrating groups acquire some cationic character with that transition step as it departs. Now, if you go back and look at equation 2334, which I can't do because this will break up, but go ahead and turn back and look at that for just a second. And what you're going to notice is the carbonyl carbon is bonded to identical groups. So when we start this particular reaction, we are using a symmetric molecule, right? So, and I may just redraw it here for you, right? We are using this guy, and that's completely symmetric, okay? So if the groups bonded to the carbonyl carbon are different and it's unsymmetric, that's when you're going to see the major product depend on this migratory aptitude, okay? And that migratory aptitude, again, is just the ease of where we see that group moving, okay? But it's going to be a really big deal when we see things that are not symmetric. So let's look at an example. Predict the major product of the reaction shown here, okay? And so we've got CF3CO3H, and so that's relatively acidic. Here's the deal. When we look at this, we know and we recognize this is a peroxy acid, okay? And we have a ketone, and so if you've got a peroxy acid and a ketone, that should indicate to you, hey, this is a Baeyer-Villiger reaction, and we are going to have an oxygen from the peroxy acid inserted between the carbonyl carbon and one of the groups bonded to the carbonyl carbon. So it's either going to insert itself here or it's going to come over and insert itself like right over there. Okay? And so the question is, which one? So this is not symmetric, right? So the question is, which one is it going to be? So in this case, that carbonyl carbon is bonded to a primary alkyl group. So this is a primary alkyl group, okay, and a secondary alkyl group, okay. And so the secondary alkyl group right here has greater migratory ability, right? So it is more likely to move and the oxygen be inserted there. And so our major product would be that guy right there. Okay, so that's how we can use the migratory ability to predict the major product.